Okay, so this video is going to delve into metallic bonding in a little bit more depth and talk about really the only trend that you need to be aware of for metallic bonding, which is melting point. So if we do a quick review, we should be aware of the fact that a metallic bond is best described as the electrostatic attraction between, and electrostatic attractions are always attractions between positives and negatives, positive and negative charges. And so in a metal, the positive charge is what we call the positive ions from the metal atoms, and the negative is the delocalized electrons between them. So the electrostatic attraction between positive metal ions or positive metal cations, and the delocalized valence electrons between them. Now, you probably don't have to say between them. You probably don't have to say valence, but you should be pointing out that you've got positive ions and you've got delocalized electrons. Those are really important to get the mark when you describe a metallic bond. So metals have a very loose hold on their outer electrons. So when you have a sample of a metal, the theory is that the valence electrons are so loosely held that they can actually move between all the different metal ions. And the metal ions take regular positions, and so we refer to them as having like a lattice arrangement. So metals do have a regular geometric arrangement of their metal ions, but the valence electrons can move between them and have no permanent location. So the valence electrons are delocalized. Metallic bonding therefore can be described as non-directional, since the attractions are not between any two particular metal atoms. Each metal ion is actually attracting to a bunch of different electrons in all directions all the time. And I don't know why this thing on ionic bonding is here. That's a failure of copy and paste. And it's different than a covalent bonding, where it is highly directional in nature because you have two atoms bonding with each other, sharing electron pairs with each other. So it's a very different model of bonding than how we believe metals stick together. So we've talked about some of the properties of metals before. They conduct because the electrons are delocalized and therefore can move. They have very good conductivity of heat as well. They're very good conducting heat. They get hot very fast because of that freedom of the metals and the electrons to move and for their kinetic energy to increase when heat is applied. They are malleable, which means that if you apply a force to them, the metal atoms can actually slide past each other without repelling apart, because even when they're changing positions, the attractions between the metal ions and the delocalized electrons remain in place. So it allows metals to be shaped and not breaking apart. And there's a final property of metals. It's a bit harder to explain, but metals have luster. They are shiny. And that's because all those delocalized electrons can absorb and re-emit basically all the wavelengths of visible light. So they just tend to like reflect light off of them in a way. That's why they appear shiny. And it's actually a very important property of metals. It's why we like them so much. At least a lot of metals like gold and silver and copper. But anyways, the point of this video is on metallic bond strength and melting points. So this is a table in the data booklet. It's table 7. It lists melting points on the top of each box and boiling points on the bottom of each box. So there are two melting point trends that you're expected to be aware of for the metals. And the first one is, what is the trend in melting point for metals across period 3? So period 3 means row 3 of the periodic table. That means starting with sodium. And the metals are just sodium, magnesium, and aluminum, because after aluminum, you get to silicon. Silicon is a metalloid. It's in between a metal and a nonmetal, not considered a pure metal. So the only 3 elements you really have to talk about a melting point trend for are these 3 for going for the first melting point trend. And if you look at the melting point, it goes from about 98 degrees Celsius, a little below water, to 650 degrees Celsius to 660 degrees Celsius. And while that's kind of a funny trend, it's a big increase and then a little increase. The general trend for going left to right is that the melting points go up. Okay, we're going to explain that on the next slide. For now, I just want us to recognize that that is the trend in the data. across from left to right, melting point goes up for these metals, and we're going to have to try to explain why that is. The other trend that you're expected to be aware of is what is the trend for melting points down group 1? So group 1 are the alkaline metals, lithium, sodium, potassium, rubidium, cesium. So you are expected to be able to explain this trend. And if we look at the melting points, we got 180.5, about 98, about 63, about 39, about 28. So they're definitely dropping. So as we go down the group, melting point of these metals goes down. Yeah. Okay. So in terms of atomic structure, we should be aware of what's happening to atoms as we look across the periodic table or down the periodic table. That was from our last chapter. So as we go left to right, we have the same number of principal energy levels, but increasing protons. So we know that that is happening in things as we go left to right. And as we go top to bottom, we know that we are increasing the number of PELs. And so that means atoms are getting bigger. Okay. All right. So let's go on and try to explain these trends. So the melting point trend across the period from left to right, the simplest way to explain it is that as you go from left to right, we know that we're getting more protons in the nucleus, but we're also getting left to right. Atoms have more protons. Atoms have more valence electrons. And so when you have these elements bonding, as you go from left to right, there's a couple of reasons why the melting point goes up. So reason number one, the number of delocalized electrons increases. When you have a metal doing metallic bonding, the number of delocalized electrons increases as you go from sodium to magnesium to aluminum. And the more delocalized electrons you have, the more attraction you're going to have holding all these particles together. It's like you have more glue in between the ions. So you can see this is an example of a group 1 metal, this picture here, and this one is group 2. There's more electrons, there's more negative electrons in between all those positive ions, and that's going to help the positive ions hold on to each other. So the number of delocalized electron increases, which equals greater electrostatic attraction, / you could also just say greater metallic bond strength. So the more delocalized electrons there are, the greater the attraction between the positive ions and those electrons. And the other thing that goes along with this is as you have more valence electrons becoming delocalized, you also have a higher charge on the positive metal ions, right? So things in group 1 only form +1 ions. They only have one valence electron that becomes delocalized. In group 2, you get 2 delocalized electrons per atom. You also get a 2+ ion. And one of the rules about charge is that more charge will create stronger attractions. So higher charge on the positive metal ions, once again, equals greater electrostatic attraction / greater metallic bond strength. So there's really two distinct reasons why, as you go from left to right, the metallic bond strength is increasing and therefore the melting point is increasing. You could probably even go and try to make a third case, which is that the atoms / the ions are decreasing in size, in radius, as you go left to right. And if they can therefore get closer together, and the closer they get, the stronger the attraction. It's not probably the primary reason that I would give. I think these top two reasons are better. But these are the general rules. These increase metallic bond strength, and therefore they increase melting point. In terms of melting points down a group, we're looking at lithium to sodium to potassium, rubidium, cesium, francium. Okay, and the general idea here, we know that going down a group, we get an increase in the number of principal energy levels, and therefore an increase in atomic radius. Okay, slash, we'll say atomic slash ionic radius. And just like in the periodic trends topic, when the positive charge, this positive ion, is more shielded by more principal energy levels, then there's less of an attraction between the positive ion and the delocalized electron. So there's more shielding effects between the positive charge of the positive metal ions and the delocalized electrons. And so that equals a lower electrostatic attraction or weaker metallic bonds. So the bigger these atoms are, remember the positive charge is all at that center point, that center nucleus, and you can see that as the atoms become much, much bigger, there's way more electrons shielding that positive charge. So the delocalized electrons that are on the outside of those core ions are not going to be as attracted. So as we go down the group, we get weaker attractions, weaker metallic bonds, and so the metals become softer and they melt more easily. There's also increased reactivity that we talked about before, but that's not the trend we're looking at right now. We're looking at the tendencies for the melting point to decrease. And so those are the best explanations that I can give for these two properties. You need to know melting point across period 3 and down a group, and these are the reasonings behind those trends.